This next stuff, right, there's presentations online. We will talk more about it. This is where stuff gets conceptually difficult. I think, and I'll need to kind of think about it tomorrow. So be checking out for an announcement. I might either ask you to bring your laptop to class on Wednesday, or I might have us work meeting a computer lab or something. And then we'll figure that out, right? So just be looking at that because this thing is really hard to do unless you kind of sometimes seeing is believing, right? It's kind of hard to conceptualize exactly what some of these things mean, right? So what we're talking about is a sampling distribution, right? And I mentioned this a little bit already. So I have some distribution of heights, right? Now, if the average height, right, the mean height, let's say, of men in this country is 5'10", right, which is 70 inches, right? You would assume if I said, let's look at all, instead of just all the men in the country, let's look at all of the groups of 5 men, right? And then within those 5, right, let's say we got, all right, 1, 2, 3, 4, 5, right? We measure each of ourselves. We add our heights together, we divide by 5. I write that down, right? Then I do other groups. And some of these other groups might lap, right? 1, 2, 3, 4, 5, right? That's another group, right? Average them together, add them together, right? Got another one, right? I could eventually do this for every group of 5 people in America, 5 men. That would be a huge number of groups. It would be something like 5 million choose 5, right? Even way more than 5 million, right? So we're already talking trillions of groups, right? It's a lot of things, right? So let's not try to focus too much on the number, but let's just imagine those groups. What would you think if I look at the mean of each of those groups, right? I'd expect it to be the mean of men overall, right? Does that kind of make sense? Right? If I take groups of 5 men and take their mean, the mean of all of those means, right? Some groups will be taller, some will be shorter on average, should be 5'10", right? But the standard deviation, right? Remember, I'm looking at a distribution of distributions. It's kind of weird. This is what we call a sampling distribution. We would expect that to be smaller, right? Because while there, right, you can imagine you're walking down the street, right? Maybe you see someone who's 6'6", right? Like, oh, that person's pretty tall. But how often do you see a group of people, right? Let's assume people are randomly distributed, right? I mean, like there might be a basketball team walking down the street, right? Where all 5 people, the next group of 5 people are all have an average of 5'6" in height. That's much less likely, right? Do you see what I'm saying? Meeting 5 people who average 6'5" as opposed to meeting 1 person who's 6'5", right? Do we get that? So their variation is less. So that's the standard deviation, right? So the mean would stay the same, standard deviation would decrease, right? So what are our learning objectives here, right? Sampling distribution of a statistic. I kind of just talked about one, right? So a sampling distribution of a statistic is if I take all the samples of a particular size, right? N equals 1 is just the normal, is just the thing that we normally think about, right? What's the distribution of everyone's height? What's the standard deviation of everyone's height, right? But I could take pairs, right? So me and Frank, we both share our height. Then we average it, right? Me and Isaac do the same thing. Every pair of 2 men in the whole country, we do that, right? I have a whole bunch of means. That would be an example of a sampling distribution, right? How are those means distributed? Right? So we're now talking about statistics, right? Because we're talking them about not all the data, just some of it. And how are those statistics distributed, right? Is it a good estimator for the whole population? Another thing that we haven't really talked about, right? We mentioned it briefly, but there wasn't much you could do with it when we were not doing sampling distributions. We're talking about the proportion, right? So here's your proportion, right? Say it's 50%, right? Let's say this is the proportion of Americans who prefer the color red to the color green, right? It's half and half. What would be, how often then would a group of 10 people, how often would that group have 60% preferring red to green, right? So these are proportions you can look at. So that's an interesting thing. So when there's a yes or no, a binary state for each person, right? For a group of state, there's a number, proportion, right? Percent that voted for a particular candidate, something like that. So down the line, right, we want to figure out, hey, if I collect a sample, is that sample representative? Right? So we kind of want to look at this. So imagine Drippy, right, collects a random sample of 200 Americans and then finds the mean number of states that they visited is 10.1. The standard deviation, the number of states they visited is 5.1, right? We want to then know, use that eventually, right? We won't do this in this chapter, that's the next chapter, but to be able to do that, we have to kind of consider these distributions, right? We want to know down the line, right? Is this a good estimation for the population mean? If I want a percentage error, if I want to have like a 95% error of actually, if I want an interval that actually covers the mean, right? How big does that interval need to be? What can we say about the standard deviation, right? So we're kind of thinking, how can I use statistics, right? A statistic on part of a group to help estimate a parameter, the whole group, right? So we can't really do that reverse process calculate exactly, but what we're going to start out is kind of doing the opposite thing, which is harder intuitively to think about, right? If, let's suppose, the mean, let's say this is the truth. These are the population statistics, right? It turns out if I go to every person in this country, the mean number of states they visited, 10.1. The standard deviation of number of states they visited is 5.1, right? How often, what's the probability that a randomly selected group of 10 people will have a mean that's more than 12 states? How often will a group of 300 people have a population have a mean of visiting more than 12 states, right? What will be, how often will that standard deviation be a particular number, right? That's something that we're looking at. So here are the answers, right? One of them is very convenient, right? Sample proportions, right? So if 60% of the country saw a recent movie, right? On average, groups of 10 people. On average, on average, 60% of that group or 6 people will have seen that movie, right? Sometimes there'll be more, sometimes there'll be less. If I put a mark, right, if I make a giant histogram, right, for each group, the center, the mean, right, of those proportions will also be around the actual proportion for the whole country. Same thing, right, for means, right, if I did something like that, like when I've been describing with the height. This is a really hard idea to get your head around, so I'm just trying to give you enough time to think about it, all right, before I start giving you homework and things on that, right? So here is an example, right? Hopefully we're all paying attention to this and not working on other homework or even my homework. That's not how. So here's the weird thing though, right? And we'll do this with dice. I might actually have us do this, right? So let's say you have a sample procedure, right? You have a giant set of dice rolls, right? So if I roll the dice, I have 6 possible values, right? Is any one of those values any more likely than the other one? So what do we call that distribution where everything's equally likely? We had this histogram. That was one of the things. I would say it might be skewed. It might be normal. What was the other one? Uniform, right? So uniform is a histogram where everything is the same height, right? Okay. Now, if I wanted to find the mean, right, what number is in the center of all of these numbers? If I added these up together, right, all my ones, all my twos, all my threes, all my fours, all my fives, all my sixes, and I divided by how many I have, right? Well, I get one each of these 1/6 of the time, right? So the average of these, the mean of these numbers is 3.5, right? Do we agree that that is the mean? It's also the median, right? It'd be the center. If I rolled the dice many times, this would be my average roll. Do we agree with that? Okay, so this might be, right? Let's say this might be some distributions of size 1, right? So if I want to do a sampling distribution, let's choose size 2, right? So these are going to be uniformly distributed. They're going to look like that, right? Definitely not a normal distribution, right? But let's take some of the pairs, right? This won't even be the entire sampling distribution, just part of it. Let's look at the average. So the average of 1 and 3 is 2. It's 4.5. This is 4. 2.5. Right? Notice each of these is a sample, right? And each of those has a mean. Now, do we think certain means are going to be more likely than others? I would think so, right? Because we're not going to get a mean of 1 very often because both rows would need to be a 1, right? We're going to get a mean of 3.5 a lot more often, right? Because there's more ways we can get a mean of 3.5, right? I could have a 1 and 6, a 2 and 5, right? So if I plot each of these, if I make a histogram of these means, it will no longer be uniform. It will start looking like this, right? But while it will no longer be uniform from 1 to 6, the center around it, would we expect that to still be 3.5? Do we kind of see that, right? The average, we're taking, and notice this is weird, right? We are taking the mean of data sets and getting a whole bunch of different numbers, right? Then we are plotting those numbers, right? So we're taking a distribution, then we're taking distributions from in that distribution and plotting those, finding statistics about it, right? So I'm looking at the means, right? The mean of the means is still 3.5, but the way those things are spread around is different, right? Do we get this? So this is why the normal distribution is cool. If you do this, regardless of what size n is, well, the more, or it becomes more and more normal. The bigger I make n, right, the more this is going to look like this as opposed to this, right? And that's regardless of what distribution I use in the beginning, right? That's the central limit theorem. We'll talk about that later. But the idea, I just want you to get the idea of the process that we're doing here, right? And I think I'll actually have us do this to help us understand it a little bit stronger, all right? Is that a little, it's confusing, but are we starting to get there a tiny bit? Okay, just give me blank looks. That's fine. All right, I will see you guys on Wednesday. Think about this. Try reading this section, right? Read 6.3. That will help you really get into what we're going to be doing. I'll look at what you asked, and I'll email. Oh, you got it? Okay.